fine with me.
Okay, yeah. So welcome everyone. Good day. Today we have the speaker from Technical University of Denmark, Professor Yiqi Dong. Yiqi received her PhD degree from Peking University in 2007. It was a joint degree with the Chinese University of Hong Kong. After that, she did a postdoc at the Institute of Mathematics and Scientific Computing at the University of Graz under Professor Michael Hindemüller. In 2010, she worked in Helmholtz Centrum München. Then she joined the Technical University of Denmark in 2013, and now she is an associate professor there. Her research areas include mathematical imaging, inverse problem, and variational methods, matrix application and computation, and optimization methods. The title of her talk today is Model Error Methods, CT Reconstruction with Uncertain View Angles. Yiqi, it's your time. Okay.
Thank you, Raymond. And also I would like to thank the organizers for invitation and also for organize such a nice seminar to set this activity, then for the researcher in OneWorld to meet and to discuss, exchange, share their new ideas. It's really great. Today, I would like talk a bit about model errors in inverse problem, which is a topic I'm quite interested in recent years. And the application example here I use is CT reconstruction with uncertain view angles. It's a joint work with my colleague, Professor Pierre-Christian Hansen and Nikolai Ries, who was my private PhD student. Now he's postdoc in our cookie project. So let's start with a few words on inverse problem. Of course, then we need set up forward problem first. So basically in a forward problem, we try to calculate the state of a physical system with given physical properties. Yeah. Then the inverse problem basically is going backward. We measure if we have some measurement. Then we, according to the measurement, we try to estimate those physical properties. Yeah. Inverse problem usually is related with indirect measurement. Yeah, basically, if we cannot measure those physical properties directly, then the way to do is we measure some related properties. Then according to the relation between them, we try to estimate those by solving an inverse problem somehow. Inverse problem have quite some applications in different fields. For example, if we want to study the sun, study the earth, study inside of the bodies, we need indirect measurements, right? And also like if we want to track the radiation in nuclear power plant, that's also need indirect measurement that we need to solve inverse problem. And in this talk, the application I mainly focus is computed tomography, so CT. Here I show 4 pictures with a different kind of CT scanner. The first is just a lab scanner, and it's one from our 3D imaging center in our university. It's mainly used for research. This one is a medical scanner from legal hospital, yeah. And this one is the industrial scanner. It's from Force Technology. And this is a CT scanner for underwater oil pipe, yeah. And basically those pipes lie on seabed. Yeah. It's an industrial use. And the last one here is a synchrotron. And the picture is from Europe synchrotron radiation facility. And this one was in use from last year, August, I think around. basically they generate high energy synchrotron X-ray. Then they can reconstruct images from meter down to nanometer scales. Really great. Yeah. And what's the principle of CT? I guess many of you already know. So basically we have the object here, and we from the source send X-rays through the object. On the other side, we put a detector to detect the damping of X-ray. Yeah. The mathematical model for CT we can write as this. As a linear model. I have this. Yeah, as a linear model, and G is a sinogram, and R is a Radon transform, which shows the line integral of the attenuation coefficient in the object, and F is the attenuation coefficient. And the CT reconstruction, which is an inverse problem. So basically, we want to estimate attenuation coefficient F from the sinogram G. Yeah. And here is an example. It's what we did in our 3D imaging center. We put a mystery digging kit in CT machine, and then we reconstruct the trailers inside. And then after you do the reconstruction, then you can rounding, and then you can estimate the volume of each trailer, for example. Yeah, this is CT. So now let's talk a bit about the model error. In 1979, a statistician, George Box, in his book, he wrote, all models are wrong, but some are useful. So it means all models involve some model errors. But where those model errors come from? According to this paper, here I will mainly discuss three sources which leads to model error. The first is model inadequacy. So basically, in real world, the physical process usually can be very complicated. But in order to model it, to solve it, very often we need simplify. So to get a simplified mathematical model. Also, in many applications, in fact, the complete physical process, in fact, is not fully known. Then this also would introduce some discrepancy between mathematical model and physical process. And for this type of model error, we would say it comes from model inadequacy. Another reason here is I wrote is a code uncertainty. So after we get a mathematical model, then we need to solve it. Very often we use computer. In order to use computer, we need to implement it. For implementation, which we need to discretize our problem. So this definitely would introduce discretization error, which is also kind of model error. And also, in order to implement efficiently, we may use different way of implementation, which also can introduce some model uncertainty. And another reason can be parameter uncertainty. So in forward operator, very often there are some parameters, but we only know those parameters with limited accuracy. So this limitation would introduce some model error. And in this talk, I will mainly focus on parameter uncertainty. If we back to CT, the main application problem I will talk about in the talk is uncertain view angle in CT scan. And we can formulate the problem like this. Here I consider a discretized form. So B is a sinogram, which is a measurement. And A is a discretized Radon transform. X is unknown, so what we want to reconstruct. And theta bar here is a true view angle. In some case, we do not know it. What we know is some expected view angle, which may be not identical to the true view angle, can have some uncertainty. And we call this expected view angle, we call as the nominal angle. So then the true angle can be considered as perturbed nominal angle somehow. And E is a measurement noise, which is it's random. Here I use a brief figure to show. So this is the object, here is the source, and here is detector. And there, in CT scan, maybe we have some uncertainty on the angles. Yeah. In synchrotron or medical CT scan, uncertain view angle, in fact, not really a big issue because there the system is quite well calibrated. But in industrial CT scan, that really can be a problem because, for example, what I showed, this underwater CT scanner, there definitely have uncertainty on the view angle. And another potential application would be the patient movement. In fact, patient movement in CT scan can be translated to uncertain view angle together with uncertain geometric parameters. For example, the parameter for object center and detect center. Yeah. If we include those parameters also into theta, then we can formulate patient movement problem with the same formulation. Yeah. Then we also can use same method to solve it. Okay. And there are many methods to study how to reduce the influence of measurement noise to get good reconstruction. But not so many methods to study the uncertain parameter influence. No. So, but those model errors, in fact, it really matters. Here I use a simulation to show. This is a ground truth. It's a grand phantom, ground truth. And here is a sinogram. And if we know the true angle, then we can get reconstruction by solving, for example, this minimization problem. Here, the data fitting term is coming from the assumption of the measurement noise following Gaussian distribution. And we use total variation as regularization, and we can get almost a perfect reconstruction. But if we do not know the true angle, we only know nominal angle, which is slightly different to the true angle. So it means there are model errors in our forward operator. Then if we use a similar reconstruction method, we only can get such quality result. So because the model error, the quality of reconstruction here is not really good. Yeah. Then what can we do with the model errors? How can we reduce it? In this talk, we consider a linear inverse problem. So here is our linear system. B is the measurement, and A bar is the true model, which is unknown. What we know is the nominal model. And the true model can be considered as the nominal model with perturbation. And this perturbation, in fact, is to show the discrepancy between the true model and the nominal model. If we define, if we define delta A times X as a new term eta, and if we ignore the dependence of eta on X, then we can just combine eta with measurement noise E, write as a combined error term mu. Then mu can be just considered as a measurement noise. Then we have many methods to get to the reconstruction. But then the reconstruction result won't be very good. It just exactly as what I showed in the simulation example before. So basically here, if we do this, it's same as we ignore model errors. Yeah. To take model error into account, there are several types of methods. The first type I introduced is a deterministic approach. So for deterministic approach, we consider this linear system. So here delta A can be considered as a perturbation. The first type of this kind of approach is a total least square method. And the idea of total least square method basically is we try to minimize the model error and the measurement error such that the linear system still satisfies. This type of method mainly developed by linear algebra committee. And according to a perturbation theory, there are many beautiful, very beautiful theory study on it, especially study about the bound of the reconstruction according to the model error and measurement error. There are many good theories. Another type is robust optimization. For robust optimization, basically the idea is to solve this min-max optimization problem. And here G is a semi-norm. And from this maxima operator on this constraint, we can see basically the idea of our robust optimization is to try to solve the inverse problem with the worst case of model error and bounded by lambda. Yeah. Okay. A very interesting result in robust optimization is under some condition, we can prove this min-max problem is equivalent to some classic variational method. So basically it's equivalent to the minimization problem, which include data fitting term and classic regularization. It also shows basically in robust optimization, we similar use regularization technique to handle model errors. There are also other type of method. Here I just simply list here like robust least square method, basically to combine the idea of robust optimization and the total least square method. There are also some interesting work from recent years here, and basically we add a partial order assumption on forward operator, then they build a very nice theory about the model error reduction. But we had tried to use those this type of method on CT reconstruction with uncertain view angle, but then it's somehow equivalent as add up and lower bounds on forward operator. But that in CT applications not very helpful to reduce model error influence. Yeah. Another work is this one. It's to dealing with a specific type of model error. Basically, in when we implement forward and adjoint operator, due to the efficiency of implementation, maybe we would use different models, which can introduce the mismatch between forward and its joint. So this, of course, is also kind of model error. So from code uncertainty, and there are some methods to handle this. So deterministic approach, the advantage is they can be solved very efficiently and also can handle large scale problem. But there are also issues. The main issue is it's very difficult to characterize the model errors. We know really little on model error, on structure of a model error. And also for this type method, usually model error reduction is just by applying regularization technique. That's sometimes not enough. Yeah. Another type of method to handle model error is Bayesian approach. So basically, the linear system we consider here is B equals this, and eta equal delta A times X. So basically, eta is showing the discrepancy between the true model and the nominal model. We call eta as the model discrepancy term. And we assume we know the distribution of eta. As far as I know, the first paper proposed model discrepancy term is from this paper in 2001. And the advantage to use model discrepancy term is now the uncertainty is only in eta and E. And the forward process now is fixed. But the drawback here is it's very difficult to estimate the distribution of eta, and the eta also depends on X. Then there are many ways to handle this, to use model discrepancy term. One main method I would like introduce here is approximation error approach. This approach was first proposed in 2005 by Capio and Samsolo. It's for dealing code uncertainty. So basically the discretization error. And AEA method, in fact, had been used in many applications and also had been proved used by different techniques and applied to like EIT, to photoacoustic, to magnetic particle imaging in many applications. And the idea of EAE is we assume we have a prior. We know prior distribution of X, then we can draw a sample of X. Yeah. Then if we know delta A, then according to the sample of X, we can calculate the sample of eta. Then if we assume eta follow Gaussian distribution, that's very normal. Then we can use the sample mean and the sample covariance to approximate the distribution of eta. Then if we get the distribution of eta, which is Gaussian distribution, if we also have the noise, Merriman noise, follow Gaussian distribution, then we can get the distribution of the combined error term, nu. Then if we know the distribution of nu, then we can get the posterior of this linear system together with the prior of X, of course. Then after we have posterior, then we can calculate conditional mean. At the same time, we also can get uncertainty on X. So advantage here is pretty clear. So in AEA, basically the model error is really taking into account. It's come to here. Then by marginalization, we have the model error be considered in posterior. Yeah. And also model error depend on X, which is come from here, because eta, the sample of eta is calculated by multiplication of delta A times sample of X. So it's really dependent on X. And also, after we have posterior, we can get conditional mean of X. Of course, we also get uncertainty on X with respect to model error and measurement error. That's very good. But the drawback is, first, this prior distribution of X is very important, because the sample of model discrepancy would depend on X. So this distribution must be very informative. Second, the second limitation is here to get a statistic property of from posterior with to get conditional mean that can be very expensive. Yeah, computationally expensive. Another issue can be delta A, sometimes it's not available. Yeah. So to overcome those limitations, we introduce another type of approach we call it's a combination of deterministic and Bayesian approach. And here we mainly handle parameter uncertainty. So basically, we have this true parameter in forward operator is unknown. What we know is only nominal parameter. And because we do not know the true parameter value, then of course we cannot directly in the same way to calculate the sample of eta as what we did here, because we do not know delta A. Yeah. Then what can we do? We suggest to give assumption on the parameter distribution. So we assume we know the distribution of theta. Then we draw the sample of theta. Then from the sample of theta with a given X, we calculate the sample of eta, which is it's different as AEA, because in AEA here, we calculate the sample of eta according to the sample of X. Here, we calculate the sample of eta according to the sample of model parameter. And the X here is given. And then after we get sample of eta, then we can do similarly. We calculate sample mean and the sample covariance. Then we still assume eta follow Gaussian distribution. Then we can get Gaussian distribution of combined error term. Then we can come to this linear inverse problem. And in order to incorporate more advanced prior information of X and also reduce the computational complexity, instead of conditional mean, here we use map estimate for reconstruction. Then we iteratively update the, we can see the sample mean and the sample covariance of eta and the reconstruction X. This combination approach first was proposed in 2019. Then after that, we had another 2 journal paper on this type of approach. This one is a PhD thesis from Nikolai, and this one is a master thesis from Frederick in our group. And in this master thesis, instead of consider uncertain view angle, they consider uncertain geometric parameter in CT scan, but with a similar way. Okay, now we're back to CT problem. Then I will introduce the method more specifically. Okay, give more detail. So CT reconstruction with uncertain view angle, we can formulate the problem like this. And here, theta is a view angle. Yeah. The goal here is we want to reconstruct X from the sinogram with unknown true view angle and measurement noise. There are some previous work on this specific application problem. I still separate as two types. The first type is a Bayesian approach. Basically, there it's in Bayesian framework. They set the view angle theta as a hyperparameter. Yeah. Advantage with the Bayesian method is we can estimate X and theta at the same time, simultaneously. And also same time, we would get uncertainty of X with respect to the errors. But the drawback would be the computational complexity. It's much more time consuming. Yeah. And also this gives limitation to apply large scale problems. Another type of method, I call it a deterministic method. And here I separate as another two types. The first type is just a two-step method, which means we first estimate view angles. Then after that, according to estimated view angle, we do the reconstruction. So advantage here is that both steps can be solved very efficiently. For example, for estimate angle, we can use, there are many different technique, like we can use a reference object, or we can stick markers. And for reconstruction parts, there are many reconstruction methods for CT. And so both steps can be solved very efficiently, and also we can use it. We can really handle large scale problem. The drawback here is because it's a two-stage, so the error in estimation of view angle would continue influence the reconstruction result. We call it error propagation. To avoid error propagation, there are another kind we call joint method. So basically we estimate theta and X simultaneously. Good point here, of course, we avoid error propagation, and also is still efficient, can handle large scale problem. But the limitation is now the problem become nonlinear and non-convex. Yeah. Then the result would depend on the initialization, depend on the numerical method. So yeah. So now come to combination approach for CT reconstruction with uncertain view angle. Here we come to this linear system. We introduce the model discrepancy term eta. And here I list the assumption to just make more clear in our method. The assumption is we need give assumption on the distribution of theta in order to get a sample of theta. And this distribution is not necessary to be Gaussian. And we assume we know the distribution of measurement noise, which is a Gaussian distribution. Okay. Then we also assume the model discrepancy term eta follow Gaussian distribution. And then because E follow Gaussian distribution, eta also follow Gaussian, then we have this combined error term, mu also would follow Gaussian distribution. Then for the reconstruction part, we use this variational model. So here the data fitting term comes from marginalizing the errors, combined errors. So nu here is the mean of nu, and L is the Cholesky factor of inverse of covariance of nu. Basically, we marginalize the error term. And for regularization, we use total variation. And in this minimization problem, I think it's pretty clear most time consuming part is to get this Cholesky factor of inverse or covariance matrix. But we found if we assume all view angles are mutually independent, then covariance matrix, in fact, is just a block diagonal matrix. Then we can split this data fitting term into Q small size data fitting term. And each would corresponding to a specific view angle. Then it's much smaller size to calculate. Then we can use stochastic optimization method to solve it efficiently. So now come to the algorithm. Basically what we do here is we first we give the initial guess of L and nu. For example, we can from start we can just assume only measurement noise. Then use that as initialization. Then we get a reconstruction. Then after get a reconstruction, we draw a sample of theta. Then according to the current iterate of X, we can calculate the sample of eta. Then we calculate sample mean and the sample covariance. Then get mu and L to update the least square term in variational model. Okay. Then we alternately update X and also L nu. Yeah. That's the algorithm. So let's look at numerical result. Here we use 2D fan beam CT geometry, and we use a small example and a large example. Small example, in fact, it's an overdetermined problem with very small standard deviation. And large example, it's image resolution is 512 by 512. And the underdetermined rate here is 18%, so very low. And standard deviation in view angle is 1 degree, pretty large. So we compare 3 methods. The first one is ours, what I just showed. The second one is the one we solve similar model, but we only we use nominal angle. So basically we ignore model error. The third one is the best scenario. So here we use a true angle. Yeah, basically the best result we can get with by solving this problem. Okay, so have look at reconstruction result. The first row is a small example with a shape login phantom. The second row is a large example with grains phantom. So the first column here is show the reconstruction results by using nominal angle. So we ignore model error here. The last column is show the best scenario with a true angle. And in the middle is our method. I think it's pretty clear to see the improvement after we take model error into account. Okay. And here is few plot. This plot is relative error with regularization parameter. And from here we can see, so yellow one is our method, the blue one is best scenario with a true angle, the red one is the one with nominal angle. And we can see the optimal lambda to our method and to the best scenario, basically they are same. Yeah. The reason is that in our method, we take a model error into account. And for the one with nominal angle, we can see optimal lambda, in fact, a bit larger. The reason is we need to use a higher regularization in order to reduce the artifact from model error. This plot is to show the relative error with the number of samples, because we need draw sample of eta, yeah, model discriminator. And from here, we can see basically if we have the sample number is equal or more than 100, more or less the final result is similar. Yeah, there are no improvements. So that's why we just simply cite the number of samples equal 100. This one is a show convergent history. Because in our method, we assume view angle, they are mutually independent. Then we can use stochastic prime dual hybrid gradient method to solve it. We compare this one with the prime dual hybrid gradient method. So where in each iteration, we need to handle the full size of covariance matrix. And by using stochastic solver, we can see the method basically stop before the other method finish the first iteration. And here we compare epochs. So one epoch it means one multiplication of a forward or a joint operator with x. So another thing we can see is this is the best scenario. Yeah, and here is the result of our method. There's still room between. So there's still room to improve. Can we improve more? The limitation in our method here is one is we assume the model error follow Gaussian distribution. Second, we only marginalize the model errors. We're not really reducing model errors. So if we really reduce model error, then if model error becomes small, then of course this Gaussian distribution assumption also not influence much. So in order to reduce model error, we need to update view angles. That's why we introduce another method to include view angle estimation. Compared to the previous method, the main difference is in assumptions is here. So here we need to assume view angle follow Gaussian distribution. In previous method, it doesn't matter. We just need to know a distribution. Doesn't matter which type of distribution. Here we need to assume it's a Gaussian distribution. Then if we assume theta follow Gaussian distribution, and if we also know the combined error term follow Gaussian distribution, then we can write down the joint distribution of theta and nu. So nu is a combined error term. Then we can write as this. Then take the independence between measurement error and theta and eta. Then we can split the term, write joint distribution as this. So in this distribution, mu theta, delta, those are from the assumption of distribution of view angle. That is given. Okay. And this is from measurement noise, that's it given. And from previous method, we know we can use the sample mean and the sample covariance of eta to get the two term. And similarly, if we can draw sample of theta, sample of eta, then we also can use the sample cross correlation to approximate this. Okay, then we get all of them. Then we can just write down the conditional mean according to joint distribution. We can, according to, these two formula to update the view angle and the variance of view angle. Okay, so now we come to a new method. The main difference compared to the previous methods is it's this part. So I highlighted with orange color. So we add a view angle estimation step. So here we draw the sample of theta according to the current estimation of distribution of theta. Then we calculate the sample of eta. Then we calculate the sample mean, sample covariance, and the sample cross correlation. Then according to the previous formula here, we update the view angles. Yeah. After we get updated view angle, then we use previous method, use the new angle to get the reconstruction. Then we alternately update view angle and reconstruction. So that's the new method here. So how is the result? Now let's have a look at result. We still use fan beam, 2D fan beam, and we consider one small example and large example. Larger example is exact same setting. And for small example now, it's an underdetermined problem. So underdetermined rate around 80%. So here is the CT reconstruction result on small example. The first one is with nominal angle, so without ignore. So basically here we ignore model error. This is the result from previous method. We can see the improvements, it's very small. The main reason is now it's an underdetermined problem. So it's small ill-pose. It becomes much more difficult to the previous method. And here is the best scenario. And this is a result from the new method. Visually maybe not so clear, but if you compare relative error, so we can really see the difference. And the new method gave more or less the same relative error compared to the best scenario, even a little less, even a little better, yeah. Here is a large example. Here is more clear. So basically we can see the new method gives almost the same quality result as using the true angles. And for the angle estimation, and here I show is on y-axis is to show the difference between the estimated angle and the true angle. So if it's close to 0 would be the best. Here is in this figure is a prior, so and we can see as input the initialization. In fact, we use nominal angle, so it's not so close to the true angle, and the bar it shows 99% confidence interval. But after use our method, we can see the estimated angle is really close to the true angle and with very small uncertainty. And here is a few plots to learn from regularization parameter. In the first row here, it's a relative error to with regularization parameter. And we mainly focus on this blue line and the green line. Green line is the new method, blue line is the best scenario. And we can see when lambda is large enough, basically they behave almost same. So the reconstruction result is more or less similar. And of course, when lambda is extremely large, then all four methods would give similar results. The reason there is because when lambda very large, then the regularization become very important, then likelihood doesn't matter, right? But when lambda is very small, our method not as good as the best scenario, because when lambda very small, the reconstruction quality is not very good. Of course, with the alternating system, it would influence the estimation of angles, that also influence on the reconstruction. So to understand that, to see how robust our method to the quality of reconstruction, we show the angle estimation with regularization parameter. So basically, when lambda is very small or very large, we know the reconstruction quality is very low. Then, of course, that would lead to large errors in angle estimation. But on the other hand, because of this long flight part, if you can see, if you agree with me, this long flat part, it also shows our method, in fact, pretty robust to the reconstruction quality. So the angle estimation in our method is very robust to the reconstruction quality. Okay. Now come to the conclusion. So basically, in this combination approach, we combine variational method with a sampling idea from Bayesian framework. And we use map estimate to incorporate a more advanced prior information on X, and also to reduce the computational complexity. And we, in our method, is alternately update reconstruction and view angles. The limitation is, of course, the reconstruction. If we have start with very bad estimation of X, then would influence to the whole algorithm. But after we, in fact, we also can see after introduce view angle estimation, the whole method is pretty robust to the quality of X. And also another limitation is in each outer iteration, we need to solve one TV-based reconstruction. Yeah, that's the main cost. For future work, one thing we really would like plan to do is for now we only numerically show the convergence of the algorithm. Of course, we also next step we would like theoretically to prove it. And it's also very interesting to extend our method into other applications and also to test on real data. And another thing we are looking into is the distribution of distribution assumption on model discrepancy, because for now we assume it's a Gaussian distribution, but maybe we can find a better assumption on distribution. If you are interested in our work, you are welcome to check our paper. And also if you are interested in our project, Cookie project, you are welcome to visit our webpage. And thank you very much.
Okay, thank you, Yiqi. So now is the question and answers session. And if you have question, you can either use the raise hand button and then I will unmute you and you can ask Yiqi directly, or you can type your question in the chat box. Any questions? Maybe I ask the first question. So Yiqi, you mentioned that so the view angles must be mutually independent. So what exactly does it mean?
So basically, for example, you have for scan angle, if we set like a 90 scan angle, then this 90 scan angle, they are independent to each other. So the second angle not depend on the value of the first angle. Yeah.
So I still don't catch it. So so what do you mean by independent here?
So somehow we assume the view angle, they are not related to each other. Like we do not see like if you have equal distance, this would be dependent, right? Because we assume they all have the same gap between the angles.
So then in your test, you use 0 to 90 degree, right? So
yeah.
So then how do you take the sample?
That's 90 angles. Yeah.
90 angles. So but then they are not equally spaced.
No. No.
I see.
The nominal angle is equally spaced, but the true angle is has kind of uncertain, has a bit different as the nominal angle. Basically, in simulation, what we did is we set equally spaced nominal angle, then we add uniform distribution on nominal angle to get a single realization as a true angle somehow.
Okay.
Yeah.
Okay. So, any questions from the audience? No other questions?
I saw Amy.
Oh, there's a question. Oh, yeah. Emily. Okay, so yeah. So Emily, you can speak now.
Hello.
Hello, Amy.
How are you doing?
Good.
Nice talk. Thanks. It was very interesting.
Thank you.
So actually, yeah, this is a very interesting problem, because I work in the medical CT, and especially for cone beam CT, oftentimes there's error in the calibration because the gantry is wobbling as the patient is scanning. So one thing I was just kind of wondering though, like some of the model error is not that critical. I mean, I guess is related to the assumption from the last question. So if you had a constant error in the angle, like where all the angles are shifted by 1 degree, for example, you're going to have an error in the image, but it's not a critical one because all you've done is just rotated the image by 1 degree. It's still it has the same utility. So I was just wondering if you had thought about any kind of analysis where you discount that kind of error where it's not a real, all you're doing is you're just like either shrinking the object or rotating it or.
In our problem here, basically it's the true angle, in fact, is have kind of uncertainty. It's compared with the nominal angle. So it's a follow kind distribution. It's not just by adding 1 degree to rotate it. So to each angle, in fact, have different difference compared to the nominal one. Yeah.
Okay.
Yeah, that's why we need to add this give assumption of the distribution on theta. Yeah.
And so there's a distribution of the angles, like so I can have it. I can imagine like say a Gaussian distribution on the actual angles. But what's the impact of that on the system matrix? Because that I have a hard time visualizing.
Yeah. In basically, for example, here you're when we gave this distribution assumption on view angle, the mean here we use it's simply the nominal angle. Yeah. Then of course the important would be the variance. Yeah, how large variance. And to choose this variance, the important part is the variance need to be large enough in order to ensure true angle fall into the, like a 95% confidence interval. Yeah. Otherwise, you wouldn't have chance to get a good estimation of true angle. Yeah.
Okay. Well, thank you, Yiqui.
Okay, Jim, you can speak now, Jim.
Okay, thank you, Raymond. Thank you, Yiqui, for an excellent talk. I was wondering if you consider, so you can put regularization on the object X. Does it make sense to also maybe include regularization on the theta parameter as well?
To add regularization of theta, I think so. Basically, it's especially when we update. The things in the reconstruction step here. In fact, the theta is a kind of a given. If you also consider you add a regularization on theta, then it means you also consider theta as a variable here, or no? If theta is a variable, then this is non-convex, also nonlinear become. Then would back to that joint method for model calibration that introduce new difficulties. What we try to do to estimate view angle basically purely from sampling. Yeah.
I see. Yeah. Okay.
Yeah.
Thank you.
Yeah. And in fact, in our paper, we had compared this method with one from joint method, where they use optimization method to estimate theta and x simultaneously. Of course, then you have a nonlinear, non-convex problem. And we compared these two methods, and also we try to understand the advantage to use the sampling here. And what we observed is, of course, the objective function where with respect to theta and x, there are many, it's a multi-mode. So it means there are many local minimizer. For joint method, very easy, the angle estimation just fall at the local minimizer. But with sampling here, we saw pretty often we are not limited. We are not blocked at the local minimizer because it's not a solving optimization method. So there are advantage here. It's quite interesting. We also want to understand a bit more on this. So it's still ongoing work. Yeah.
Okay. So any other questions? Okay. If no, then thank you, Yiqiao, and thank you for everyone for listening to the talk. So I'll see you next week. Bye-bye.
Bye.